Something called a vapor pressure. Vapor pressure is exactly what it sounds like. It's the pressure exerted by the gas above a liquid. So we have a liquid here. Above it, you're going to have gas molecules. Those molecules will push down on the liquid, creating a pressure. So this vapor pressure will push down on the liquid. Now this diagram is in your book on page 392. That in a system at constant vapor pressure, so we have a vapor pressure that's constant. If we have that, an equilibrium will exist between the vapor and the liquid. Rate of evaporation of liquid equals the rate of condensation. So remember, condensation is just when you go from a gas to a liquid. You have condensation on a glass. You have like little water droplets. A dew is condensation. So it's a constant dynamic equilibrium that keeps going back and forth, back and forth. Now let's look at what happens if the temperature of the water increases. Then its vapor pressure will increase. Because the vapor above that liquid, there's more vapor coming around. Those molecules are they're moving much quicker and thus creating more pressure. Now when that vapor pressure equals the atmospheric pressure pushing down on it, the liquid will boil. So here in this diagram, the bubbles cannot form since the vapor pressure is less than the atmospheric pressure. But once there's enough kinetic energy in here, we move around a lot, we're moving around so much and so much kinetic energy, the vapor pressure is going to increase, thus can overcome the atmospheric pressure and push away, break free, break through. We're free. The little molecules are free and they can go because the atmospheric pressure, which was keeping them down, are now too weak to withhold the vapor pressure. Let's look at this boiling atmospheric pressure according to how much atmospheric pressure is out there. Now at sea level, we have the most atmospheric pressure, what we talked about at the beginning. At top of Mount Everest, there's less atmospheric pressure because there's less atmosphere pushing down on you. So there's much more atmosphere pushing down at you at sea level, so the pressure is greater. Now let's say we are heating some water, and that water is 70 degrees Celsius. Atmospheric is going to be greater than its vapor pressure at this point. So the bubbles of vapor cannot escape. The atmospheric pressure is pushing down too much. The vapor pressure is too weak to withhold it. But if we start heating that up even more, say, okay, we're not going to take this, we're going to heat this up 100 degrees. Let's do this 100 degrees Celsius. We're going to give them enough energy, the molecules enough energy, so the vapor pressure is going to equal the atmospheric pressure, and thus the molecules can break free. So at the boiling point, vapor pressure is equal to the atmospheric pressure, whereas before the atmospheric pressure was greater. Now vapor pressure is greater, or excuse me, vapor pressure is equal to atmospheric pressure. It can start boiling at 100 degrees Celsius at sea level. But at Mount Everest, where there's much less atmospheric pressure, the water will boil at a lower temperature because there's less atmospheric pressure. So there doesn't need to be as much vapor pressure. The vapor pressure can be much less. Doesn't have to be as strong. So since the vapor pressure can be much less, things will boil because it will boil 70 degrees Celsius. Atmospheric pressure is not as great. So you've probably, if you've gone skiing and stayed at a lodge way up there, high altitude, you've probably you could boil water at a much lower temperature. But because of that, you're not able to cook as fast. You want to cook, things will cook much quicker if it's a hotter temperature. You will not be able to cook as quickly. You can have your macaroni, got your macaroni and cheese, but if it's 70 degrees Celsius and you're trying to cook your noodles up there, it's going to take much longer. So one way that people try and get around that problem is adding solutes, such as salts. That will increase the vapor pressure. That will increase the boiling point. But most people at very high altitudes will have pressure cookers. That means they increase the pressure, almost like an artificial atmospheric pressure. They increase this, which will then cause the vapor pressure to have to be higher, thereby causing the temperature to have to be higher in order for it to boil. Now, this graph is similar to that one on page 394, figure 13.9. Now, obviously not everything has the same boiling point. Obviously not everything has the same vapor pressure. So here we have vapor pressure in torrs. That's another unit of pressure in temperature Celsius. It'd probably be best just to look at these as kilopascals. So really, we don't really need to memorize any of these numbers. Just to understand the significance. If we have 1 atmosphere of pressure here, that's the same as 101.3 kilopascal. But this is where boiling will occur, at this line. And we can see they magnified water. So water occurs at 100 degrees, diethyl ether, at maybe 35 degrees, benzene, ethanol, around 75 degrees. We can see that the vapor pressure is much less, so at these points, since they have a smaller vapor pressure, these will boil at much lower temperatures. The vapor pressure is going to be higher, they will have a higher boiling point. So small vapor pressures, they'll have a smaller boiling point. So for example, these are some boiling points of some substances. Carbon disulfide has a boiling point of 46 degrees. That has a much less, or a much smaller vapor pressure than water. Water has a high vapor pressure compared to all these other things. Ethanol is basically alcohol. That's the alcohol that's in booze. That has a smaller boiling point. It's much more volatile. It will go into a vapor much easier than water. So all these things will go into, they have a lower vapor point, thus having a lower boiling point. Since they have a lower vapor point, they will go into vapor much easier. So oftentimes, if you're sick or something, your parents will put a cold compress on your head. Water will take heat away. Now they'll also, at times, they'll put some alcohol, usually propanol, not ethanol, take rubbing alcohol and put it on your forehead. That will evaporate much quicker, much easier than water, and takes heat away much quicker. And that's because it has a lower vapor point, lower vapor pressure, and lower boiling point. It goes into vapor much easier. Now we're going to look at changes of state. Let's first define sublimation. Sublimation occurs in solids when the vapor pressures will exceed atmospheric pressure at or near room temperature. So not only does the vapor pressure equal atmospheric pressure, so we get boiling, but it's greater than atmospheric pressure. So what happens is you have a solid and it doesn't go to liquid, it goes right to gas. So here we have some iodine molecules doing that. Dry ice, carbon dioxide, solid carbon dioxide will have this where the vapor pressure is so much greater that it doesn't waste time with the liquid phase. It goes from solid right to gas. Normally solid, liquid to gas, but this time we forget about it. With sublimation, we go right to gas. Phase diagrams are important. This is page 403, figure 1315. Now, phase diagrams will show the relationship between pressure and temperature in all the states, physical states, solid, liquid, and gas. You can have phase diagrams for really anything. This is a phase diagram for water. If we look at this, we have At this point, this is atmospheric pressure, 101.3 kilopascals. And here we have 100 degrees Celsius, which is boiling. So if we go right up here, at 101.3 kilopascals, we have boiling at 100 degrees. At zero, at atmospheric pressure, we have the melting point, which is also the freezing point at 0 degrees. If we change the atmospheric pressure, so if we're going up in elevation, we're going to decrease our atmospheric pressure. What's going to happen to the boiling point? These lines here will show you the difference of when, or at the point when liquid, for instance, will change to vapor, or vapor to liquid. This line will show you when solid changes to liquid. If we have a low atmospheric pressure here, that means we're going to have a lower boiling point, because this is when we hit vapor. This is when it boils at this temperature. If we have a very low atmospheric pressure, we're going to have a much higher boiling point, much lower boiling point. The vapor pressure is going to be much lower. If we have a much lower atmospheric pressure, we're going to have a much lower boiling point. That's because of the vapor pressure is not going to be needed to be as high. We don't need as much kinetic energy to change the vapor pressure. Now what happens here? So what happens here at 0.61? At 0.61 kilopascals and at 0.016 degrees Celsius, what happens? We're going to get to something called the triple point. So at the triple point, at this precise point in water, all three phases will exist in equilibrium. So that's magic there. We have liquid, solid, and gas all existing at this triple point. We have to have the right combination of temperature and pressure. What happens if we have very high pressure? If the pressure is very, very high, that means we're going to have a very high boiling point of water. The temperature is going to have to be so much higher, so it makes the vapor pressure so much higher in order for that water to boil. We can even look at freezing. At 0 degrees Celsius, atmosphere will have a melting point or the freezing point. Same thing. How could we cause water to melt at a lower temperature? Well, if we want water to melt at a lower temperature, let's say we want water to melt below 0, we'll have to raise the pressure. At this point, the pressure is going to have to be so much more in order for that, and I didn't draw a straight line there, unfortunately. So there we go. In order for that water to melt at a much lower temperature, we're going to have much higher pressure. If we want a solid at a lower temperature to freeze at a lower temperature, we're going to have to lower that atmospheric pressure. The phase diagram is actually pretty interesting. You can kind of play around with it and say, well, what happens if we increase the pressure outside? Well, it's going to cause the melting point to go up. It's going to cause the boiling point to go up as well, because this is where we go from liquid to vapor. This is where we go from solid to liquid, or from liquid to solid. Now what happens if we really decrease? That's going to increase the freezing point or the melting point, and it will decrease the boiling point, as is demonstrated when we go high in elevation.